Okay, so we're now on part 2. And when we report results, we often are mostly focused on the main statistic, the means or differences in means or correlations between two things. But the variance is really very important because it determines how precisely we can measure these. And a good experiment is one in which we minimize variance due to unwanted factors. And sample size is a major determinant of this. It's not the only determinant. As we'll see, there's other things that affect it. But we're going to focus here on how sample size does affect that. And we're going to use the little script that we used in session 1 to demonstrate this. In session 1, I suggested that we should set the difference between two means to 0. So we were actually saying there's nothing going on, it's just a completely null effect. And we were then interested in simulating data and seeing how often you got false positives, particularly in situations where p-hacking was possible. But now we're going to use the default settings where the mean group difference is an effect size of 0.3, and you've got an n of 20 or 100 per group. And these are all things you can change. So I've got the script loaded here. And what this script is going to do is go through with these two sample sizes, just reminding you 20 or 100. This is the effect size, which you can change if you like. And you run it repeatedly in a loop. In fact, I've got it running now 20 it runs, this little loop just sets the sample size to 1 or 2, and it makes a PDF name and sets up a PDF to hold the pirate plot outputs. And then when you actually run it, it runs 20 times and generates, I'll just show you this. Here we go, right down to here. I'm going to stop at line 48. It thinks about it a bit. And then you'll see, in fact, I should have set my working directory before running it, which I didn't do. So I'm not quite sure where my PDFs are going to end up, but we shall see. Here we go. Let me check where my working directory is. The get working directory command is good for that. It is where I had hoped it would be on the folder which I've got for this work. So we'll go there for the moment and look for it. And we should see a couple of PDFs which hold the output called pirates. Here we go, just created. And that's what one of them looks like with n of 20. I'll show you this on slides, it's easier to see, but you should have things created just like this. And for each run, you're getting the distribution of the two groups where you have in advance set the true effect size to be 0.3, so that the pink group should be higher than the blue group. And just eyeballing this, you can see that sometimes that's true, but sometimes it's not. Let me return to my slides. Get out of here, and out of there, and go back here. So, so I'm suggesting that you run and you get these files. And this was just when I did 10 runs to make it a bit easier to see. You can see already that this is as it was previously, that you've got quite a lot of cases where there's no significant difference if you're using P of 0.05 between the two groups. This one is a big difference, this one is, and this one is, but there's many runs where there's really no, and here's one where the means look really very closely similar and the P is extremely high. So in general, you're really only seeing anything in about 2 or 3 of runs out of 10. And this is really worrying. If you're running an experiment like this, it would mean that you would be missing a real effect. You'd be making a type 2 error in this occasion. If we then look at what happens with when there's 100 per group, things are somewhat better, but they're not still 100%. You're not always picking up this group difference of 0.3. Here's a run where, in fact, the pink is a bit lower than the blue. And so you can see that, and here's another one. So you can see that although you've got a higher chance of seeing a real effect with 100, it's still far from perfect. So the points I want you to pick up from this is that your smaller samples are associated with more variable results, But if you've got small sample sizes, true but weak effects will usually not give you a significant result. So here, with an effect size of 0.3 and a sample of 100, we got a significant result on about 60% of runs. And that's the same as saying that the power of the study to detect an effect size of 0.3 is, I've put 0.60%, but it's either 0.6 or it's 60%. I'll have to correct that in the slides. But most statisticians recommend power should either be 80%, should be 80% or more, although it may depend on the purpose of your study. So this is really sobering news because it suggests that a lot of studies that are done are underpowered. When you run the script, and I'm going to suggest you spend some time on it because this is really quite key that you get this idea, you might like to compare the values you obtain with these power tables from Cohen that I showed you previously, which just show you the sample size per group that you need for two-tailed 0.05 or one-tailed 0.025 significance, different levels of power and different effect sizes. And you will find that they do broadly agree. So the simulation is doing what you would hope. It's giving you accurate estimates, particularly if you run thousands of simulations. So the thing to try on your own then is to play with the exercise and then try the lines from code from lines 59 onwards, because that code, previously we ran it with a null effect and it showed you this very flat distribution of p-values that you get. When the null hypothesis is true, the expectation is that all p-values are equally likely. What you find when you put in a real effect is that that distribution shifts and becomes negatively skewed. Or is it positively skewed? It becomes positively skewed, I think, yes, because it's like a sort of skewer going out to the positive end. And in other words, the p-values are bunched up towards zero, become closer towards zero. But what you will see is that that skew is rather weak. It's induced very weakly with small sample sizes and small effect sizes. But you need to play with that to get a sense of how the p-value distribution shifts with those variables.